For our first video of Chapter 4, I'm going to talk about balancing reaction equations and a concept known as stoichiometry, which is basically using the coefficients from a balanced equation to figure out the amounts of products that will be produced in chemical reactions. So first, I'm going to just I'll write out a chemical equation, and I just want to talk about it, identify several of the key elements. So let's go with something like this. Okay, so first and foremost, when looking at a chemical equation, to the left of the arrow, these are the reactants. So when you hear me use the term reactants, that's everything to the left of the reaction arrow. And those represent the materials that you start with in your chemical reaction, so the things that you actually mix together in the very beginning. To the right of the arrow, these are your products, things that are produced in the process of the chemical reaction. Right here in parentheses after each molecule, you see, in this case they're all a G, but this is your state of matter. So this is saying that these happen to all be gas. They don't. That doesn't have to be the case, but you either have gas, liquid, solid, or something that you'll see quite often, which is aqueous, which just means that it's dissolved in water, and that'll actually come up later on in this chapter. So it's a state of matter. Here we see these twos in front of the oxygen and the water. Those are your reaction coefficients. So the term coefficient, that just means any number in front of a molecule. If you don't see a coefficient, like for the CH4 and the CO2, you can just assume that its coefficient is 1. And that just tells you how many molecules are of that type are involved in the reaction. And when we're balancing reactions, it's actually the coefficients that we're determining. And so it's very, very important. In fact, it's necessary to make sure that you have balanced coefficients before proceeding with any kind of calculations about the reaction. If you don't have that, then you will not get the right answer. Because what the coefficients tell you, that tells you the molar ratio that all of these react and or form in. So if you recall in Chapter 3, I started talking about mole-to-mole ratios within a molecule, between atoms in a molecule and the molecule itself. Well, these are now mole-to-mole ratios between different molecules in a chemical reaction. And you need that to know that mole-to-mole ratio in order to do proper calculations. So, let's practice balancing. So, start with a relatively simple one. So let's say we've got H2 plus O2 yields H2O. I'll put the states of matter in. Gas. So now, what does it mean for a reaction to be balanced? As you can see, I did not put the coefficients in yet. For a reaction to be balanced, that means that the same number of each type of atom exists on both the reactants and product side. So, in this case, we have hydrogens and oxygens, right? So the best way to do it is I like to set up a little chart with 3 rows, or I'm sorry, 3 columns, 1, 2, 3. In the middle column, you just put every single type of atom that exists in the reaction equation. In this case, we just have hydrogen and oxygen. Now, on the left-hand column, you put the number of each of those atoms that exists on the reactant side of the equation. So far, currently we have 2 hydrogens, and we have 2 oxygens, and you see those from the subscripts, right? Since there are no coefficients yet, we don't have, because you'll have to multiply always the coefficient by the subscript. We don't have any coefficients yet, so it's just the subscripts. On the product side, we have 2 hydrogens and 1 oxygen. So when these numbers are equal across the rows, that's when you have a balanced reaction. So when you have the same number of hydrogens in the reactants and the products, and the same number of oxygens in the reactants and the products, that is when you have a balanced reaction. That's what we're going for here. And again, when balancing a reaction, the only thing we can do is change the coefficients. So, right now we only have one atom type, oxygen, that does not have that is not equal on both sides. So let's start with that. So we only have one oxygen on the product side, and we have two on the reactant side. So that means that we need to change the number of oxygens on the product side. So let's give water, the molecule that contains oxygen, let's give that a coefficient of 2. So now we can say 2 times the subscript that you don't see, because remember, if you don't see a subscript, it's 1. So 2 times 1, so now there are 2 oxygen atoms, but when we add a coefficient, you can't just look at the atom type that you're trying to change. You have to look at every atom involved in that molecule. Hydrogen's here too, so now we have a new amount of hydrogen, so now 2 times 2, so now we have 4 hydrogen atoms. That's okay, because we can add coefficients to the other side now. So now oxygen is good across, right? Now we have 2 hydrogens on the reactant side and 4 on the product side. So now we need to change this. So how are we going to make this have a total of 4 hydrogens? Well, if it's H2, we need 2 of those. So 2 times 2, we now have 4. 4 and 4, 2 and 2. The numbers are equal across. Every atom type has the same amount on both sides. This is now a balanced reaction. The last step, you just want to look at the coefficients and make sure that you can't reduce them, because sometimes if you have more complex ones, you might take a little bit of a roundabout way to get there. And so let's look into the coefficients. We have 2, 1, and 2. Those cannot be reduced. Let's say, for instance, we end up with 2, 2, and 2. Hypothetically speaking, if we got that, well, 2, 2, and 2, that ratio could be reduced to 1, 1, and 1. So if you can reduce the coefficients that you got to a smaller whole number ratio, do it. If you can't, then you're done. That is your answer. So this is our balanced reaction equation. Let's try one more. A little bit more complex this time. So I've got so let's set up our chart again. Now I've got 3 different types of atom this time. So we've got carbon, we have hydrogen, and we have oxygen. Okay, on the reactant side, we have 3 carbon atoms, we have 8 hydrogens, and we have 2 oxygens. On the product side, we have just 1 carbon, we have 2 hydrogens. Now, here you can see that both of the molecules on the product side contain oxygen. So we need to add those together. You need to add together the amount of oxygen for any type of atom from all of the different molecules that contain that type of atom on that side of the equation. So from the carbon dioxide gives us 2 oxygen atoms. Water gives us 1. That's a total of 3. Okay. So, now we can start balancing. So none of these are the same right now. Right? So, honestly, you can kind of choose which one you want to start with. Let's start at the top. Let's go with carbon. So we've got 3 carbons on the reactant side and 1 on the product side. So we need to get this up to 3. So let's put a coefficient of 3 in front of your CO2. So now there's 3 carbon here, but we changed the number of oxygens as well. So now 3 times 2, there are 6 oxygens now from the carbon dioxide. Plus, there's still this one over here from the water. So right now we're at 7. So we're good with carbon. Let's go to hydrogen. So we have 8 hydrogens on the reactant side and just 2 on the product side. So we need to get this up. So if it's every time we add a water molecule, we're adding 2 hydrogens. So let's just put a 4 here. So that makes it 4 times 2 is 8. But once again, we have now changed the number of oxygens. So we still have the 3 times 2. We still have these 6 oxygen atoms from the carbon dioxides over here. Now we have 4 times 1 is 4. So 6 plus 4, 10. So carbons are good. Hydrogens are good. Now we just need to change oxygen. So now we need to increase the number of oxygens on the reactant side. So we have O2 here. So we can put a 5 here, so because 5 times 2 gets us 10. And that reaction is now balanced. Let's double check our coefficients. We have 1, 5, 3, and 4. You cannot reduce that ratio, so that is our balanced reaction.